morning.
Good morning, Masood. How are you, sir?
Yeah, I'm pretty good now.
Good, glad to hear it.
Thank you so much, Dr. Stewart.
Okay, I have 3 minutes past, so maybe we should go ahead and get started. So, some logistical stuff that we can discuss. Homework 3 was posted last week. It is nominally due this Friday. This is the one that we went over on Monday. It has a simple computation of Pleb-Shorten coefficients like we worked on last week, and an application which is taken from the 2019 comprehensive exam. So please take your time and work through that. Let me know if you have any questions. For the schedule, there's no class this coming Monday for President's Day. And so since we don't have a lecture on Monday, we'll only have one meeting next week. It seems to me like that's a useful time to use as a catch-up week. So as you've noticed, I'm sliding about a half a lecture behind where I would like to have been on the schedule. That's more or less anticipated. It was just not clear when that was going to happen. So from my point of view, it's really appealing to use next week as a chance for me to finish up the discussion on the hydrogen atom. I think it's very unlikely that we will make it all the way through the algebraic solution of the hydrogen atom today. So we can take our time, we'll wrap up the differential equation version of the hydrogen atom today. We'll start laying the groundwork for the Runge-Lenz vector, and we can talk about the algebraic solution in its completeness next week. So if that's what I'm thinking for myself of making next week catch-up week, it makes sense to make that a catch-up week for you guys too. So I'm inclined to assign a new homework for this week, post it on Friday as usual, but not have it due next week. Give you guys 2 weeks to finish it. That way, people who need a little extra time to catch up on back homework assignments have some time to do that. That's what I'm currently thinking for next week. What do you guys think? Is that a good plan? Do you have any questions or concerns?
I think that's a pretty good plan. I was a couple minutes late to last week's, or I guess last lecture.
Yes.
When did you want us to get the homework corrections to you before the solutions are out? What was the time limit that we had?
No. So I don't know how you would give me corrections before I post the solutions. Otherwise, you wouldn't necessarily know how to fix what you did wrong. So
yeah, that's kind of what I was thinking too.
Yeah, no. So the corrections you are welcome to submit anytime, I guess. I don't have any hard cutoff on that between now and the end of the semester. Sooner is better, but I can't post the solutions until everyone has submitted it the first time or until I stop accepting initial solutions for a given homework. But after I have everybody's submissions, I will turn on the solutions so you can all see them. And then after that, feel free to correct your work and you can resubmit it to get some points back.
That sounds awesome. Thank you.
Okay, great. Any other logistical questions or concerns? Yes, sir.
Yeah, so you haven't released the solutions yet, right?
I've turned on the solutions for homework 1 because I have all submissions for that. I have about 8 out of 14 was the count that I had on Sunday for homework 2. So I have not turned on the solutions for that. So once I either have everybody's solutions or if it drags on so long that I feel like I have to cut it off, then I will make those solutions visible to everyone as well.
Okay, so are you still going to accept the corrections for homework 1?
Yes, absolutely.
Okay.
So take your time. You can submit corrections on homework 1 anytime.
Okay, realize that I made a mistake with my screen coordinates.
Yeah, no problem. Yeah, so feel free to go back and you can fix that, resubmit it, and you can make up to half of lost points.
Okay, and also, I don't know if you talked about this Monday, but have you changed your office hours?
I talked about the office hours. I mentioned the point that you raised that there's that 30-minute overlap with StatMech. I haven't changed anything formally yet. If that becomes a problem for you guys, let me know and I can shift the timing around. Okay. Any other logistic stuff that you guys want to discuss? Okay, cool. If not, then let's remind ourselves what we were talking about on Monday. On Monday, we wrapped up the leftover stuff on operators carrying angular momentum. And that put us about a half a lecture behind for discussing the hydrogen atom by differential equation, the brute force method, as I would call it. So today we've got the second half of that, and then we'll start the first half of the algebraic solution, which employs the Runge-Lenz vector and introduces another conserved quantity that we can use. It looks a lot like angular momentum. So let's remind ourselves the differential equation stuff that we started with last time. We were solving the Schrodinger equation for the hydrogen atom. You can start with the Schrodinger equation, the time-independent Schrodinger equation in 3 dimensions in terms of the Laplacian. If you write the Laplacian for the kinetic energy in terms of spherical coordinates, all of the angular stuff gets completely absorbed into the angular momentum operator L squared. And this reduces the problem down to an effective one-dimensional Schrodinger equation. You have minus h bar squared over 2 mu. Here I'm calling the mass mu to avoid ambiguity with the magnetic quantum number m. D squared, dr squared. You have an effective centrifugal barrier potential. This is the rotational kinetic energy associated with possessing finite angular momentum. This is just L squared over 2I, the moment of inertia of a point particle. It acts effectively as a repulsive correction to the radial potential, the central potential. For the Coulomb problem, the central potential is an attractive potential minus E squared over R. E is the charge of the proton. The electron has charge negativity. So you have a competition between an attractive 1 over R potential and effectively a repulsive 1 over R squared centrifugal barrier. So setting this up, this is a one-dimensional problem in the radial probability amplitude U. This is a transformation of the wave function. If you square it, this gives you the probability per unit R. And this definition absorbs a factor of R from the volume element in spherical coordinates. The next thing that we did was we defined natural variables in the problem. We defined a length scale, A, corresponding to the energy. This is basically the wavelength of a particle having energy E. In terms of those natural units A, we defined a scaled or dimensionless length variable R tilde. And correspondingly, we converted the dimensions that enter into the potential into another factor lambda. So in terms of these scaling variables, we had d squared dr tilde squared minus 1. The minus 1 came from the energy. And then we have lambda e squared over r, L plus 1 over r squared. The next thing that we did was we analyzed the asymptotic behavior of this differential equation. Yes? Question? Yes, sir. So the part that exists classically does carry over to quantum mechanics. So the fact that you have a 1 over r potential in the classical Coulomb problem also appears quantum mechanically. There are also new quantum mechanical effects in addition to this. So we will talk about corrections to this simple Coulomb potential. Those go into the fine structure and the hyperfine structure of the hydrogen atom. We will discuss those corrections after we discuss perturbation theory, which is the next topic after the hydrogen atom. So I think if it has a classical counterpart, yes, it carries over to quantum mechanics. Also, quantum mechanics has some other stuff that's all its own. Okay? Sure. Okay, the next thing that we did was we looked at the asymptotics of this differential equation. We studied the differential equation in the limit, let's say r goes to 0. Formally, this means that that dimensionless parameter r tilde is much less than 1. When r goes to 0, you see that 1 over r goes to infinity and 1 over r squared also goes to infinity. But even though they're both going to infinity, 1 over r squared goes to infinity faster. So in the short distance asymptotics, the centrifugal barrier potential dominates. And the behavior is completely controlled by the value of the orbital angular momentum L. In this limit, we found UL of R twiddle scales like R twiddle to the L plus 1. That came from taking this differential equation, throwing away the unimportant pieces, and solving the behavior of the dominant term when R goes to 0. We also looked at the opposite limit, R twiddle going to infinity. This is the dimensionless parameter R twiddle much greater than 1. And in this limit, we found that for bound states, UL of R goes like e to the minus R twiddle, decaying exponential. We also discussed the unbound states, the continuum states. They behave like a plane wave. But for the purposes of continuing the rest of this discussion, we're going to focus only on the bound states. So if we know, so maybe let me add this caveat, for energy less than 0. And I should also say that this equation already specified for energy less than 0. Otherwise, it could have been plus 1 or minus 1 here, depending on the sign of the energy. Okay, so once we know both the polynomial behavior as r goes to 0 and the exponential behavior as r goes to infinity, we want to explicitly remove that known behavior from this differential equation and write a differential equation for the part that's left over, which we don't know yet. So with this in mind, we wrote down the form of the solution. UL of R is equal to, treat it like a definition, the large distance asymptotics e to the minus r times a polynomial function VL of r. This is the polynomial part. And from that short distance asymptotics, we know that the polynomial behavior starts off with this power of r. This is the most important power of r when r goes to 0. There can be higher powers of r that are going to 0 faster than this, but the polynomial can't start with 1, for example. That would contradict this asymptotic behavior. R twiddle to the L plus 1. Okay, so when we plug in this form into the differential equation, what we found last time was that the differential equation can be recast into VL double prime minus 2 VL prime plus lambda e squared over R twiddle minus L plus 1 over R twiddle squared VL equals 0. And so now we've gotten a simpler differential equation that we can try and solve for the polynomial piece alone. To incorporate this information, we want to start with a power series onsides. This is very similar to what we did for the harmonic oscillator. We found the large and short distance asymptotics. We removed the known asymptotic behavior. And when we had no other good ideas, we tried a series onsides. And that's what we'll do here. When all else fails, try a series solution. And try and figure out what the coefficients are. So this unknown function VL of R is equal to some series over coefficients. This thing starts off with R to the L plus 1, and on top of that, there can be any number of powers of R with unknown coefficients. So times sum from j equals 0 to infinity, unknown coefficients C sub j, R twiddle to the power j. And so this incorporates both features of the known asymptotic behavior. The exponential behavior at long distances, the leading polynomial power at short distances. And that set of unknown coefficients is everything that we still have not yet figured out about the differential equation. So this is sum j equals 0 to infinity, Cj, and then the total power on R is R to the L plus j plus 1. So now I want to take this series onsides and plug it into here. And we're going to try to develop a recursion relation between the coefficients. That will determine the structure of the power series. All right, so my differential equation is in terms of V prime and V double prime. So given that V, let's calculate its derivatives. If VL is sum j 0 to infinity, R to the j plus L plus 1, C sub j. Then VL prime is sum j equals 0 to infinity, Cj, j plus L plus 1, R to the j plus L. VL double prime is sum j equals 0 to infinity, Cj, j plus L plus 1, j plus L, R to the j plus L minus 1. Just direct power rule applied to this series. All right, now let's plug it back into the differential equation. So starting off with VL double prime, my first factor is sum j equals 0 to infinity, Cj, j plus L, j plus L plus 1, R to the overall power j plus L minus 1. That's my V double prime going in here. Minus twice VL prime is this one. Let me maybe draw a line here to separate out what I'm doing. Minus sum j equals 0 to infinity. The overall factor is 2 Cj, j plus L plus 1. And the power is R to the j plus L. All right, that's this one. Now I've got some overall factor times VL. Note, however, that these come with different powers. So my VL has some polynomial power in R. This one is going to subtract 1 from that power. This one is going to subtract 2 from that power. That's going to be good because that's going to make it compatible with either this term or that term. So coming from the first term here, the 1 over R potential, I get plus sum j equals 0 to infinity, lambda e squared c sub j, and the overall power is r to the j plus l. Because I had j plus l minus 1, and when I divide by r, I remove one of those powers. So that takes care of this one. And the last one involves the centrifugal barrier, minus sum j equals 0 to infinity, L plus 1, C sub j, and the overall power is R to the j plus L minus 1. All of this stuff equals 0. So now I've got this one, and I've got the equal 0. So the part that's nice about this is that after we've removed all that asymptotic behavior, now I have two compatible terms in this recursion relation, right? I take two derivatives, I get minus 2 in the exponent. You remove 2 powers of r. That combines nicely with the centrifugal barrier, which didn't take derivatives, but it did divide by r squared. For that reason, this exponent from the kinetic energy piece and that exponent from the centrifugal barrier piece are now of the same order, and we can combine those coefficients. Similarly, the first derivative that came from product rule when we expanded out with the exponential here has one derivative that subtracts 1 from the exponent. That combines nicely with the 1 over r from the attractive potential. So this one combines nicely with this one. This is what's going to make it possible to solve it as a two-term recursion relation. Okay, so if I collect the overall powers here, I have sum j equals 0 to infinity. In the first term, I have c sub j. Let's see, I want to put that together with this one. So I have c sub j times, let me move my bracket, I guess. That's the easiest way. C sub j times j plus L plus 1 minus L plus 1. And this multiplies the power r to the j plus L minus 1. And then I'm going to write this as plus sum j equals 0 to infinity e sub j. Let's see, the positive power is this one, so let me write that term first. And the e squared minus 2 j plus L plus 1. R to the power j plus L is equal to 0. So all I've done here is I've combined those terms and I've combined these terms. Let me make sure I didn't follow any factors somewhere. I think I'm good. Okay, I'm almost done. The idea with the power series solution is that I need to get all of the powers together. I want to make this power the same as that power. That way I can say, for example, if I have, a plus bx plus cx squared plus blah, blah, blah equals 0. All of these coefficients must separately equal 0 because they come with different powers of x. Remind me, why is that true? Why do different powers of x that all add up to give you 0 must have vanishing coefficients? Linear independence. This is a vector space statement. You can never make a linear combination of x that will give you x squared with scalar coefficients because these are independent basis vectors for the function space, f of x. If the sum is 0, these are linearly independent, the coefficients must be 0. That's the idea. So to put these in the same form, I want to define a new summation index. So let me define in, let's see, which one do I want to shift? J equals k minus 1 in this term. So I want to write this and redefine this so that this term looks like r to the k plus l minus 1. And I want to redefine this term so it looks like r to the k plus l minus 1. This term, all I have to do is rename j equals k. This one I need to shift the index. So in this term, I want to define j equals k minus 1. Or equivalently, k equals j plus 1. So if I make this substitution, that turns this power into this power. I have to worry a little bit about what happens to the coefficients because these things are going to start at different orders. So if I do this slowly, in the first term, I have sum k equals 0 to infinity, c sub k. This term is k plus l plus 1. This term is k plus l minus l plus 1. This first term starts from k equals 0. R twiddle to the k plus l minus 1. Second term, now if j is equal to 0, this term starts from k equals 1. That's the mismatch. I have, this was c to the k. This is now going to be c to the k minus 1. Lambda e squared minus 2, j plus 1 is equal to k, so this is k plus l, r to the power k plus l minus 1 equals 0. So we've almost succeeded. Same power, but the series starts at different places. The mismatch is when k is equal to 0. But I'm in luck, because if k is equal to 0, then I have l times l plus 1 minus l times l plus 1. So even though this series nominally starts at 0, that first term is 0. So this thing is equal to 0 if k is equal to 0. So because of that, I can just throw out that first term and now make both series start at k equals 1. Now they are completely compatible. So now I combine both series in the same place, and I have sum k equals 1 to infinity. C sub k, k plus l, k plus l plus 1, minus l, l plus 1, minus c k minus 1, 2 k plus l minus lambda e squared, times r to the power k plus l minus 1 equal to 0. Right, does that all work out? I changed the minus sign here. I pulled out an overall minus sign so the terms are in the opposite order. Looks like everything else is in agreement. Okay, now I'm in good shape because this is a series that starts off with one power of r, next power of r, all different powers of r. Coefficients must separately equal 0. So we immediately conclude this equals 0 for any k because of linear independence. Of different powers r to the n. So that immediately lets me set this thing minus that thing equals 0, so this thing equals that thing. So I immediately conclude ck k plus l, k plus l plus 1 minus l, l plus 1 equals ck minus 1 to k plus l minus lambda e squared for any k. This tells me if I know the previous coefficient C sub k, how to immediately find the next coefficient Ck. This is the complete solution to the series. If I start off with the very first coefficient in the series, I can find all of them using this recursion relation. That is the best you can hope for when you try a series on SOTs to solve the differential equation. Okay, it's easiest to express this as a ratio. C sub k over C sub k minus 1 equals 2k plus L minus lambda e squared over k plus L plus 1 minus L plus 1. This is the full solution to VL. Once we have VL, that gives us UL. Once we put back in the exponential behavior at long distances, that also then gives us, let me write this out explicitly. UL is e to the minus r twiddle VL. And then this also gives us the complete radial dependence of the Schrodinger equation, which was UL divided by r. And then that gives us the complete wave function psi LM, which were r sub L, y LM to the angular dependence. So this recursion relation, modest as it is essentially a complete solution for the Schrodinger equation. However, it's misleading because this series, if I take it and allow it to continue to all infinity in this sum, would violate my asymptotics. This series cannot be allowed to extend to infinity. If it does, it will overpower the e to the minus r asymptotic behavior that we know must be there. How do I see that? Take the limit of this recursion relation as k goes to infinity. The large R asymptotics. That means I'm looking at the highest possible powers of R twiddle to the, what did we call it? K plus L minus 1. And so this means I want to look at this ratio in the limit as k goes to infinity. And I'm going to compare that behavior of these coefficients to the required asymptotic behavior that must be there. In the limit as k goes to infinity, this ratio ck over ck minus 1. As k goes to infinity, the numerator becomes 2k. The denominator becomes k times k minus something unimportant. The denominator is k squared. 2 over k. So maybe for the first few powers of r, this ratio doesn't look like this. But if you go high enough in the power series, every term starts to look like this. Asymptotically, that power series starts to look like the sum over k. Maybe that sum doesn't start from 0, maybe it starts from some finite power. It looks like sum over k. Every time I have this ratio, right? So I want to, how to say this? I want to get an explicit formula for what c to the k looks like asymptotically. Ck asymptotically. What I'm trying to say is this is 2 over k times ck minus 1. And ck minus 1 is going to give me 2 over k minus 1, c sub k minus 2. And if I keep using this recursion relation in the asymptotic regime, I start to reconstruct the power series that I know what it is. And it's bad. C sub k goes like, every time I repeat this, I'm going to have 2 over k minus 1, 2 over k minus 2, down the line. This starts to look like 2 to the n over k factorial. What kind of function looks like sum over k 2 to the n over k factorial r to the k? Well, this looks like exponential of positive, and I guess this is r tilde, 2r. So the behavior of this recursion relation at asymptotically large k, which corresponds to the dominant behavior at asymptotically large distances, is very positively exponential. And that's bad. Because we know that the overall behavior of this function must be decaying exponential. And if I have e to the plus 2r from the series competing with e to the minus 1r from the factor out front, e to the plus 2r wins. So the point is, if the series continues to infinity, the asymptotic behavior would be I would have UL of R goes like, or is equals, e to the minus R, VL of R, and if VL of R goes like e to the plus 2r, then overall this gives me a wave function that goes as a positive exponential. And clearly this is bad. Why is it bad to have a wave function that blows up exponentially as r goes to infinity?
Normalization?
Yeah, it would be impossible to normalize. You couldn't have a wave function normalized to 1. It wouldn't satisfy the boundary conditions. It wouldn't satisfy the Schrodinger equation when the energy is much, much less than the potential. So because of this, I must forbid the series to go to infinity. I must require that this recursion relation terminate at finite order. Let me say that the known r goes to infinity asymptotics. So let us call the maximum power of R that occurs in this finite series n. When will this thing terminate? This recursion relation must always be true. So if this thing is going to terminate, this ratio had better go to 0 at that maximum power. So if this denominator is n, if k minus 1 down here is n, then the numerator upstairs predicts k plus 1, the next power. So this would tell me Cn plus 1 over Cn if I use this formula. Let's see, my denominator is n plus L plus 1, n plus L plus 2, minus L plus 1. My numerator is 2n plus L plus 1 minus lambda squared, or lambda e squared, must equal 0. If n is the highest power. Sorry, let me maybe change this notation. I told you something contradictory here. I want n to be the maximum power overall, but the power in the series is not just k. It was k plus L plus 1 or something. Let me maybe, instead of calling this n yet, let me call this k max. We'll define n in just a second. K max plus 1, and then this is k max plus L. Okay, that's better. if Kmax is the last term in the series. Sorry about that. So I want to require the numerator to be 0. That is the termination condition for the series. So this must give me 2 Kmax plus L minus lambda E squared equals 0. Sorry, I fumbled this again. Bear with me 1 second here. So this was the relation in terms of K and K minus 1. I still want Kmax and Kmax plus 1. So apologies. This should be Kmax plus L plus 1, the same way as I had before. And then this is plus 1 and this is plus 2. Sorry about that. Hopefully we're all on the same page here. I'm talking about K and not the total power N. I'll talk about the total power N in a second, but I do want to say that Kmax is the maximum one, meaning Kmax plus 1 is 0. So clearly this gives me, I have to have lambda E squared equals 2 Kmax plus L plus 1, and this thing is an integer. So this is the combination that I want to call N. Okay, so maybe to write it a little bit more explicitly, since I fumbled it a moment ago. We said this thing has some power series solution. We said this is a sum over K equals 0 to infinity, C sub K, R twiddle to the power K plus L plus 1. If K equals K max, so the thing cannot go to infinity, it has to stop at some K max. And at that K max, the maximum power is R twiddle to the K max plus L plus 1. And that's exactly what's here. So if N is the overall degree of the polynomial, that N must be equal to lambda E squared over 2. K max L plus 1 equals highest degree of the polynomial. And this termination condition is lambda E squared equals 2N. All right, so this is the quantization condition because lambda, that coefficient, has the energy buried in it. This tells me that the energy of the bound states can only take on certain integer values associated with this N. So this is the quantization condition. For the energy. If I plug back in what lambda was square root 2 mu over h bar squared absolute value of the energy. So lambda squared is 2 mu over h bar squared absolute value of the energy. The energy is negative. So if I replace in terms of E rather than absolute value of E, this is minus 2 mu over h bar squared E. So this gives me energy equals negative 2 mu over h bar squared lambda. and lambda is 2n over e squared. Did I miss something?
Lambda squared, right?
Sorry, yes, lambda squared in the denominator. Thank you. So we have E equals minus 2 mu over h bar squared lambda squared, and this is minus mu e to the fourth over 2 h bar squared n squared. So I have a particular combination of coefficients that tells me what the energy scale is, these guys. So I'm going to call this negative E naught divided by n squared. This is the energy of the quantized level n. And the allowed values of n, k starts at 0 and up, L starts at 0 and up, so n starts at 1. And let's see, the allowed values of L, so we have this, since k is greater than or equal to 0, L is greater than or equal to 0. That's what gives us n starts at 1. And I also have n is greater than or equal to L plus 1. So what are the allowed values of L? The overall power starts at 1. If k is 0, then L plus 1 can only go up to n, is what I'm trying to say. Yeah, L plus 1 can only go up to n. So this means the allowed values of L for a given n are 0, 1, 2, up to n minus 1. All right, so what is the energy scale? The value E naught equals mu e to the fourth over 2 h bar squared. You can plug in and get what these numbers are. It's always tricky to convert between CGS units and SI units. I think it's useful here to introduce the fine structure constant, which is the same no matter which choice of electromagnetic units you use. If I define alpha E and M is E squared over h bar C. Numerically, the fine structure constant is approximately 1 over 137. So if I plug this in, I get E naught is 1/2 mu C squared alpha E and M squared. And now I can plug in standard numbers to evaluate what this is. This is 1/2, the rest mass energy of the electron is 511 electron volts. Alpha E and M is approximately 1 over 137 squared. So if you plug this in, you get the ground state energy of hydrogen, which is negative 13.6 electron volts. Okay, the other important feature to point out is the scaling of the energy levels with n. So if I plot energy of the level as a function of n, when I have n equals 1, the energy level is here. The energy level is minus E naught. At n equals 2, it's minus E naught divided by 4. So it jumps, halfway, 3/4 of the way up here. So this is minus E naught over 4. At n equals 3, it's even closer. It's minus E naught over 9. So you can see these energies follow a 1 over n squared curve, where you've got one deeply bound state, and the higher you go, they get very, very close to becoming unbound. But there's a whole lot of states up here. You have an infinite number of n, which are bound, but they are all extremely shallowly bound. So the higher orbitals of the hydrogen atom take very little energy to kick them out and make them free. How are we doing?
For the fine structure constant,
Yes.
is the numerator E, capital E like energy, or E like the charge of the electron?
It's the charge of the electron. So this is useful because different standards for electromagnetic units use different numbers and different scales for E squared, but everybody gets the same alpha, E, and M. So it's useful to convert from this thing where E is in coulombs or something like this to something which is 1 over 137, and this is mc squared for the electron.
Great, awesome.
Sure. Okay, one important feature to point out about this is that the energy levels are degenerate for different values of L. Not just of L, but also M, which is that Z component of the orbital angular momentum. So there's some extra symmetry in this problem that says different values of the angular momentum have the same energy. And with whatever time that we have left at the end of class, we will talk about the origin of this additional symmetry. It's associated with every 1 over r potential, whether that's the gravitational 1 over r potential or the Coulomb 1 over r potential associated with the hydrogen atom. How much degeneracy is there? I think it's worth calculating the degeneracy factor. At a given value of n. So we want to count up how many states are there that have the same energy. I can sum over all of the allowed values of L and sum over all the allowed values of M. L can go from 0 up to n minus 1. For a given L, M can go from minus L to plus L. And I'm just adding up 1 for every one of these states. I want to count the number of states that have this. When I do the summation over M, I get 2L plus 1. And now I need to additionally sum over L. So this is 2 times sum over L from L equals 0 to n minus 1. I had a math professor who told me a great way to remember how to do a series like this. If you compare the first term and the last term, L equals 0 and L equals n minus 1, their average value is the same as the second term and the next to the last term, right? For every pair, if you take the first one and the last one, you get a certain average. If I add 1 and I subtract 1, that average is the same. So if I imagine this series in pairs, starting at both endpoints and coming in, the average is always the same. So this is equal to the number of terms times the average value of that term. So the number of terms from 0 to L minus 1 is n of them. And the average value is n minus 1 plus 0 divided by 2. Minus 1 over 2. And then in addition, I have the 1 where I just add up n states. So, okay, cleaning this up, 2 cancels the 2. N times n minus 1 plus the extra n. The overall degeneracy factor is n squared. So there's a lot of degeneracy, especially as you go to higher states. The ground state n equals 0 is unique. The second excited state, n equals 2, is fourfold degenerate. This is not even including spin yet. Spin has just been completely irrelevant for this discussion. Spin will also double these number of degeneracies. So the feature that I want to talk about with whatever time we have left is the origin of this degeneracy and how it leads to this n squared degeneracy at every given level. Okay, that was the most important thing to point out. Other comments before we shift to the Rondo lens vector. Let's see, so now that we found everything, we can also calculate the typical length scale. In the wave function. That typical scale, we scaled out r divided by a, where that a was defined as square root h bar squared over 2 mu absolute value of the energy. Now we can plug in what the absolute value of the energy is. This is square root h bar squared over 2 mu, 2 h bar squared n squared over mu e to the fourth. And you end up with n h bar squared over mu e squared. So this typical length scale here is called the Bohr radius. So this is A equals n times A sub b, where the Bohr radius A sub b is h bar squared over mu e squared. In terms of the fine structure constant, this is h bar c over mu c squared, 1 over alpha e and n. If I plug in rough numbers for this, h bar c, there's 1 over 2 pi from the h bar. Hc is one of those combinations that I always remember. That's 1240 electron volts times nanometer. The mass energy of the electron is 511 keV. And 1 over alpha E and M is 137. And if you plug all of this in, you get approximately 0.053 nanometers. So this is the typical length scale in a wave function. Notice that the length scale increases linearly with n. So if the ground state had an exponential decay that was e to the minus r, e to the minus r tilde, that's e to the minus r over the Bohr radius. The first excited state, n equals 2, will be e to the minus r over 2 times the Bohr radius. The nth excited state will be e to the minus r divided by n times the Bohr radius. So higher excited states die faster as r goes to infinity. So the general form of the wave functions are psi n lm of r, theta, and phi. This was 1 over r VL of r over n times the Bohr radius. I guess I'm writing it here a sub b. I think the textbook also calls it a naught. A sub 0. Both notations are common. E to the minus r over n times the Bohr radius. This was the comment that I made just a moment ago, times the spherical harmonic YLM of theta and phi. This combination of coefficients where this V was defined by the series that we solved for has a name. These are called the associated Laguerre polynomials. For whatever it's worth, this combination is equal to square root 2 over n AB cubed, 1 over 2n n minus L minus 1 factorial over n plus L factorial 2r over n AB to the power L times the associated Laguerre polynomial n minus L minus 1 2L plus 1, whose argument is 2r over n AB. So this is what that overall radial behavior of the wave function is equal to. Honestly, I don't learn a damn thing from writing this down, but it's useful to compare in your textbook. If you need to look up the values of these things for the first few values, this is given in the textbook on page 357. So I don't learn any physics from this, and I won't belabor the point any further, but you can look up those first few polynomials as needed. Other comments?
I just had a question. It was from a while ago, but I didn't want to
go ahead.
Ruin anything. We were talking about the recursion relation ratio, and the important bit was that we set it equal to 0 at k max. So we just set the numerator equal to 0.
Yes.
But we didn't really do anything with solving for k max. Is k max just unnecessary? Were we just looking for the quantized energy bit? Do we not need to know what k max is?
K max is equivalent to n. You can talk about either so n was k max plus L plus 1. So you can either talk about all of this language in terms of n, the overall power, or you can talk about k max, which was the extra bit that you add on top of L plus 1. So
okay.
I think we just changed variables from instead of talking about k max to talking about n.
Right.
Okay. Any other questions? Okay, I would be remiss if I didn't mention at least a word about spectroscopic notation. When talking about angular momentum states, the L equals 0 state is, for historical reasons, referred to as S wave. And it's written as something like the 2s orbital. This 2 means n equals 2, and s means L equals 0. Similarly, L equals 1 are referred to p wave orbitals. L equals 2 are referred to d wave orbitals. And L equals 3 are referred to f wave orbitals. And that's all the orbitals that you need to describe all of the atoms that are stable. In principle, you can use a terminology like this to describe not just atomic states, but any angular momentum states. So sometimes you'll read in the literature something about S-wave superconductivity versus P-wave superconductivity. Those are talking about different mechanisms that lead to superconductivity coming from different angular momentum values that describe how it becomes superconducting. That terminology is associated with the angular momentum. There's also, including spin, there's also so-called modified spectroscopic notation. Where you label the angular momentum part by S, P, D, whatever, and then you also label the total angular momentum coming from spin and from orbital angular momentum as well. So the notation is something like 2s plus 1 capital L lowercase j. So when you are including spin and you are describing in a more detailed way what the quantum state is, you put an exponent beforehand, a superscript. This is the spin multiplicity, telling you how many states are in the spin ladder. So if it's spin 0, you put a 1 there. If it's spin 1/2, there are up and down, 2 states in the ladder. You put a 2 here. If it's spin 1, there are 3 states in the ladder. You put a 3 there. The letter that you write down here is telling you about the value of the angular momentum. So you write capital S, capital P, capital D, that's telling you about the value of the total orbital angular momentum L. And then down in the corner, you can write J, the total angular momentum combining both spin and orbital information. So this is important in describing how this state couples to an external magnetic field, for example. So down here in the corner, this is J, the value of the total angular momentum. J equals L plus S, in the same way we've talked about by adding up Pletch-Gordon coefficients. So when talking about atomic orbitals, you might see something like the 3p state. And you'll need to know how to interpret what those quantum numbers are talking about. You might see something like the 2p 3 halves state, or the 2p 1 half state. You'll need to disentangle what these quantum numbers are telling you. So in this first example, this one corresponds to n equals 3, L equals 1. That's the more familiar one. This example, this 2 is telling you about the spin in the system. This is telling you S equals 1 half. Spin 1 half electron state. Could be spin up or spin down. The P is telling you L equals 1. And if I'm going to add together spin 1 half and angular momentum 1, there are two different ladders that I can make out of this when I add them together. I can add them up together and get 3 halves. This is the J equals 3 halves ladder. Or I could add the same spin angular momentum, orbital angular momentum, and get the secondary ladder. S equals 1 half, L equals 1. This is the secondary J equals 1 half ladder. So these are all different ways that are common in the literature to describe how the angular momentum in different configurations works. I don't find a whole lot of physics in this, but this notation is important for being able to read papers and things. Okay, I think finally I am ready to spend the last 10 minutes of class talking about the Runge-Lenz vector. Any other questions before I shift gears? Okay, let me maybe start by giving a few references. There's a really nice discussion of this in Goldstein. So if you have your classical mechanics textbook, I strongly recommend you check out page 102 to 106. They'll talk about what I want to start discussing today, which is the Runge-Lenz vector as a conserved vector in the Kepler problem, the 1 over r gravitational potential. And then ultimately the form that we're going to want to really use it for to help solve the hydrogen spectrum talks about much later, pages 413 to 415, where he talks about the algebra of the Runge-Lenz vector and how it's related to angular momentum. In classical mechanics, Goldstein is talking about it in terms of Poisson brackets, but we know that Poisson brackets just get turned into commutators. Shankar also has a discussion of this. Much more limited discussion, but it is there, split up pages 360 to 361 in terms of the hydrogen atom, and coming back again, pages 422 to 423. Word of warning, different authors use different conventions for the Runge-Lenz vector. There is no absolutely standard notation. So be advised. So I think Goldstein and Shankar differ by an overall normalization factor. Other authors also differ by an overall minus sign, so just be careful. Okay, so in classical mechanics, a 1 over r potential, which corresponds to a 1 over r squared force law, has an extra conserved quantity. So again, there's different conventions for the naming of this. The one that I like is called the Laplace-Runge lens vector, which is shortened to the LRL vector. Ironically, neither Laplace nor Runge nor Lenz discovered this vector. This is the kind of thing that physicists have discovered and forgotten and rediscovered over the centuries. So if your force law, F of R, is minus K for some constant K over R squared times a unit vector R over R, of course, this implies that your potential V of R is minus K over R. So this shows why both the Kepler problem, where your constant would be the gravitational constant times the product of the masses, or the Coulomb problem, where your constant would be the charge E squared, both fall into this class. So Goldstein talks about this in the context of the Kepler problem, but everything that we say about that also applies to the hydrogen atom. So the definition of the Laplace-Runge lens vector is A is defined to be P cross L minus MK times the unit vector R over R. Okay, so what is it? I think physically the easiest way to interpret this is as an eccentricity. So this is related to the dimensionless eccentricity vector. I can define the eccentricity vector E as the LRL vector divided by something that carries its units, m times k. Right, so this is m times k times a unit vector. So m times k is the units of the LRL vector. So this quantity is P cross L over mk minus the unit vector r over r. So what does it look like? If you have an elliptical orbit in the Kepler problem, we know that the solution of the Kepler problem is ellipses in general for bound states, hyperbolas in general for unbound states. Let me consider these points to be the two foci of the ellipse. So let's try to visualize what that vector looks like at different points on the trajectory. So at this point, as your particle is moving around, its momentum vector p is pointing down. This contribution, mkr over r, points this way to the left. Let's see. Yeah, so I've got two things. mkr over r points to the left. And if p points down, the orbital angular momentum for the object which is spinning around in a circle like this, L points out of the page. So if I take L cross P, or what is it, P cross L, P cross L. P cross L is a vector which points in this direction. P cross L is this guy. So if I combine all of these things, the LRL vector A is something which is pointing in this direction. Now let's consider a different point in the orbit. Let's consider, for example, one up here at the top. Here the momentum vector P is going to the left. The radius from this focal point, which is my origin of coordinates, I'm going to have something which is mkr over r pointing in this direction. If L is out of the page, P cross L is pointing up. P cross L, your LRL vector is pointing again this way. It is conserved. Same value, same direction up there. So you can recompute this at different points in the orbit and see for yourself visually that it is conserved. The direction that it's pointing in is associated with that direction from one of the foci to the other focus. So it's pointing along the eccentricity axis of the ellipse. And the fact that this is a conserved quantity is telling you that the shape of the ellipse is stable under the orbit. If this were unstable, if this ellipse were precessing, then this ellipse would turn as a function of time. The fact that it doesn't tells you that this axis, the eccentricity axis, is constant as a function of time. So this is related to the feature of having the orbits closed. So the derivative of the eccentricity vector is equal to 0 is equivalent to saying the derivative of the Runge lens vector is equal to 0. And this is a feature which is specific to 1 over r potentials. If you have central force problems of a different kind, then in general, the orbits are not closed. They spiral around and they keep going around, and it traces out a different path every time it goes around. The fact that it goes back to itself the same time is a special symmetry of the problem related to the conservation of that ellipticity axis. Okay, in my remaining 1 minute, let me show you very quickly the fact that it is conserved. That's very easy to see. So Newton's second law for the Kepler problem is dp dt is equal to my force, which is minus k over r squared r over r. I also have conservation of angular momentum. dl dt is equal to 0. So putting these features together, if I take time derivative of the quantity p cross L, L doesn't change, only P changes. So this is dp dt cross L. I don't have to worry about product rule because L is constant. Then I expand this thing out. This is minus K over R squared, R cross L over R. Now I can open up the parentheses here because this is minus K over R squared, R cross P over R. I can even simplify that a little further because P is mv. This is minus K over R squared M R cross R dot over R. Okay, and let's see, if I do this, I get P cross L is equal to minus mk over r cubed. If I use the back minus cab rule for this, I have r times r dot product with its derivative r dot minus r squared vector r dot, and this is equal to mk r dot over r minus r vector scalar r dot over r squared. So this uses the fact that this quantity is 1/2 ddt of r dot r, which is 1/2 r squared. And then you can convince yourself that this thing on the right-hand side is just the derivative of the unit vector r over r. Take the derivative of the numerator, I get this term. Take the derivative of the denominator, I get that term. So altogether, this tells me ddt of P cross L minus mkr over r, which is the derivative of the Runge lens vector, is equal to 0. So the equation of motion for the 1 over r potential does conserve this quantity. It is associated with the conserved orbits. For our purposes, we will rescale this vector and make it look like angular momentum. This will be useful because it will play nicely and combine with the angular momentum L and act like it's a higher dimensional angular momentum. And we will interpret this as a bigger rotational symmetry in an effective 4-dimensional space. That will allow us to solve the hydrogen atom problem algebraically next week. Okay, thank you for your patience. Any other questions? Okay, if not, we'll use next week to catch up. There is no class on Monday. Feel free to email me with questions, and I will talk to you again next Wednesday. Thanks very much.